This is a third of a series of 3 talks on climate change and global warming, which I put together, prompted by a personal need to understand all the terms that are currently being bandied around, to try and get beyond the rhetoric of obviously biased parties, and to take a look at the evidence and come to my own conclusions as to the realities of man-induced global warming and how I need to react to it in my everyday lifestyle. I also wanted to create an unbiased information set which might help people make informed decisions for themselves. The talks are a compendium of the work of others. The information and most of the illustrations were taken from the internet, and I provide credits in the slides. As usual, I have a Yogi Berra quote at the bottom of this introductory slide. You can observe a lot just by watching. And I put that in here just to note that it's up to us to open our eyes in an unbiased manner, observe what is happening rather than just listening to others, and to chart a way forward. As I said, this is the third of a series of 3 talks about climate change, global warming, and its effects. Other talks in the series are causes and history of climate change, and global warming, realities, causes, prediction, and cures. And I provide the links to those talks here. In the past 2 talks, we saw that climate change is a constant and natural phenomenon, as evidenced by this record of atmospheric temperature change over the past 500,000 years, way before man had any hand in influencing the environment. We saw that the factors affecting climate change are many, their interactions complex, and are not fully understood. We also saw that the concentration of greenhouse gases in the atmosphere has increased markedly since the start of the Industrial Revolution, and that this has increased the heat retentive capacity of the atmosphere, shown here as the annual greenhouse gas index on the right. The blue line in the graph here basically shows the change in concentration of carbon dioxide since 1750, which was the start of the Industrial Revolution. And we saw that that increase has gone from about 280 parts per million up to the current 415 parts per million. The black line shows the increase in all greenhouse gases in the atmosphere, normalized as if they were all CO2. And what you see is the gap between the blue and the black line is ever increasing, indicating that significantly higher percentage of non-carbon dioxide greenhouse gases are being emitted into the atmosphere now than previously. This is important because those greenhouse gases are magnitudes more effective in the greenhouse gas effect than carbon dioxide itself. Additionally, we reviewed temperature records since 1880 from a variety of sources. All of them are in agreement in that they show the average temperature of the atmosphere at the Earth's surface is warming. This rise is not linear, as we can see from this staggered line, and this is undoubtedly due to it being affected by a variety of factors. In fact, we can see 2 apparent cooling trends, one between 1880 to about 1915, and another between 1945 and 1975. But there's no doubt about the steep warming trend observed from approximately 1975 to the present day. It's arguable that much of the recent warming is due to the increased concentration of greenhouse gases in the atmosphere due to human activity. When we talk about global warming, we need to realize that the average temperature anomaly that we see on the graphs is just a statistical construct. In fact, different parts of the world are experiencing different amounts of warming. This map shows by how much the surface temperature of different parts of the world has changed over the past 50 years. Look at the scale down at the bottom here. Basically, the hotter colors going from white through yellow, oranges, through reds into browns shows an increase in the amount of temperature change. Note the extreme increases experienced in the Northern Hemisphere and in particular in the high latitudes. Note also that while the rise in temperature is more emphasized over land, the oceans have also been warming. As shown in the previous map, the rise in atmospheric temperature over land has been higher than the rise in the oceans. However, the bulk of the oceans shouldn't be forgotten. Over 90% of the total energy change in the Earth's heat content has been absorbed by the oceans, as shown by this inset graph. This represents an enormous amount of energy. This graph is a sort of cute or alarming way of illustrating the amount of energy involved in the recent warming of the oceans. The graph here is showing the change in ocean heat content relative to an average between the years 1955 to 2010, which is shown here as 0. The change in heat content of the oceans in energy is equivalent to about 1 billion times the energy of the atomic bombs used on Hiroshima and Nagasaki in 1945. A gigantic amount of energy is stored in heat in the oceans. I'm just going to show a little video here which shows the change in surface temperature across the globe through time. The sudden increase in the very recent past is remarkable. We're just going through the years from 1880 up to the present. The blues are, it's relatively cool, and as the colors get hotter, that just indicates more warmth. You can see things are beginning to warm up now in the 1990s. And here in the 2000s, things are getting markedly warmer, and we see a concentration of the warming effect in the Northern Hemisphere. So what effects are occurring and can we continue to experience associated with the ongoing warming? This is a probability of occurrence chart. The vertical axis is probability. 0 is something will never happen. 1 is it's a dead certainty. The horizontal axis is temperature, cold on the left and hot on the right. Let's take a look at the current climate curve here. We see a temperature range from cold here to hot, these extremes in here. And we can see that the extremes have low probabilities of occurrence. The more normal temperatures in the middle have higher probabilities of occurrence. The range of temperature and the shape of this probability curve basically encapsulates what we think of as climate. Now take a look at the new climate curve in red. This is shifted to the right, corresponding to the global warming that we've been experiencing. And what we see is that the winter extremes are warmer than before, the summer extremes are hotter, and we have a larger amount of hot weather in the summers. This shift in climate, although far from clear, is connected to extreme weather events. In this slide, the strength of relationship between the two increases from left to right, from weak to strongest. There is weak evidence of global warming causing increased incidence of drought, forest fires, and tornadoes, but there is stronger evidence that the warmer oceans cause increased incidence and intensity of tropical storms, cyclones, and hurricanes with their associated storm surges. The intensity of heat waves also seems to be affected. This is a satellite image taken in September of this year showing the Gulf of Mexico and the South Atlantic Ocean northeast of South America. Here's the northern shore of South America, Gulf of Mexico over here. What we see is 5 tropical storms occurring at the same time. This is unusual and is being blamed on the warming ocean waters. Some of these cyclones evolve into hurricanes. That's Hurricane Sally. And the hurricanes appear to be increasing in intensity. And this intensity increase means that when the hurricanes hit the shoreline, they actually travel further inland and wreak their destruction over a wider area than previously experienced. Eastern Canada can expect to feel more effects from hurricanes in the future than in the past. So how warm is it expected to get? This graph, which we saw in the last presentation, forecasts a rise of between 2 to 4 degrees Celsius over the 1971 to 1999 average by the year 2100. These yellow lines indicate that we have experienced almost 1 degree of warming since 1990. The three scenarios that are shown here project a temperature increase based on various models of greenhouse gas input into the atmosphere. Low, we see associated with about a 2 degree rise, medium 3, and high about 4 degrees Celsius. So according to those models, greenhouse gases have a direct effect on what we can expect with regards to global warming. This is a map showing the distribution of that predicted warming. Like the warming already experienced, and we saw the map of, this warming will not be even across the globe. Land surfaces will warm more than the ocean surface, and the most significant warming will be experienced in the Arctic. So how will this affect us? Well, to put it into perspective, we need to realize that we're not the first generation of humankind to be affected by climate change. This slide shows the temperature records since the end of the last glacial period, around about 11,000 years ago. And on this temperature change, which is marked by this wiggly line here, are input notable human events, if you like. Up to and during the last glaciation, man was essentially a hunter-gatherer. The marked warming at the end of the last glacial period resulted in a shift toward farming, at first in the Fertile Crescent in the Middle East. The present-day Sahara was a savanna Eden with abundant game, fish, grasslands, and forests. Relatively minor temperature oscillations over the past 4,000 years impacted and arguably contributed to the demise of numerous empires and dynasties. For example, expansion of the Roman Empire about 2,000 years ago was aided by productive granaries in North Africa, in areas which today are now desert. The end of the Roman Empire coincided with the onset of a cold phase, the stress of which may have been a factor which induced migration south of the North European barbarians, and they have ended up toppling Rome. We see around about 900, the Vikings settled Greenland. They called it Greenland because it was green, but they were frozen out of it by about 1400 after the onset of the Little Ice Age. The Little Ice Age lasted until about 1850 and was marked by extremely cold temperatures in Western Europe. And this is the Thames in London, which was frozen at the time. And there are plenty of Dutch masters showing, painting pictures of Holland with frozen canals and skaters and whatever. This is the current temperature here. And just note that in the relatively recent past, there have been quite a number of times when the temperature has been warmer than we're experiencing today. Of course, it wasn't just in Europe that climate change had an effect on civilizations. Another example is the Mayan city-states of Central America in the Yucatan. And these flourished from about 500 to 900 AD, but they suffered collapse between about 1000 to 1400 AD, in large part, it's believed, due to climate change and associated droughts. The droughts affected agriculture and led to the downfall of the city-states and a profound change in the Mayan political system. The archaeological evidence of the Mayan city-states now being uncovered from within the jungles of the Yucatan by LiDAR technology, as shown in the top right here, is nothing short of remarkable. And it definitely warrants a good Google. It's just incredible what they're finding. So how will we be affected by the current global warming? This map of the world shows predicted changes in agricultural productivity by the year 2080. Greens are good, yellow to red is bad. What we see is that in the equatorial areas and mid-latitudes, they will be negatively affected by ongoing global warming. Canada, Northern Europe, and Northern China will benefit by improving agricultural productivity. So how does this translate into how people will be affected? This is a world hunger map for 2017. It shows the distribution and degree of undernourishment of human populations. Blue is good, i.e. in the blue countries, the majority of people get enough to eat. Orange, browns, and reds are progressively bad, with successively higher levels of undernourishment. This slide combines the two previous maps. It shows the vulnerability of different countries to the effects of global warming. A lot of this has to do with food availability, but also factors in infrastructure, health, etc. There's a strong socioeconomic relationship to vulnerability along with geography. It's probably best not to take this map at face value as it's based on a particularly extreme climate change model. But we should use it to remind ourselves that the effects of climate change will affect populations of countries differently, and that we in Canada will be relatively well off compared to others. This vulnerability will affect societal stability in those regions of the world that are negatively affected. And quite possibly, we're already seeing the effects. Where do you think all those people flocking across the Mediterranean come from? And what do you think is the root cause or root causes of why they're moving? We've seen that the experienced and predicted global warming is most pronounced in the high latitudes of the Northern Hemisphere. Let's look at what's happening to the icy areas of the globe, the Arctic, which is predicted to be significantly affected. Before we look at what's happening today, let's just put it into perspective as to what's happened in the past. The top map shows the world at the last glacial maximum, approximately 20,000 years ago. The bottom map is the present day. When we compare the maps, we see on top, 20,000 years ago, a markedly greater expanse of continental glaciers compared to what we have today. So we need to realize that there's been a ton of melting in the past 20,000 years. We're going to take a look at how some of this melting occurred through time in a later slide. This is a series of slides and a couple of videos to show what's actually happening today. First, we're going to look at the Arctic sea ice. And this is a remarkable movie from NASA, which is composed of successive satellite images showing the changes to sea ice coverage in the Arctic Ocean from the period 1984 to 2019. I'm going to start the movie and stop it and do some explanation here. Oops, I can't do that. Sorry. I'll just talk while we're going through. What we're seeing is in white is old sea ice, and the gray is new sea ice. And what we're seeing up here, these are the months of the year. And so we're seeing an annual cycle as the sea ice pulses south in the winter and retreats back in the summer. We're also seeing in the Beaufort Sea what's called the Beaufort Gyre, which is a clockwise revolution of sea ice in the Arctic Ocean. And this is where the sea ice is largely born, and it circulates in the Beaufort Sea, but also spins out and goes out of the system through the Fox Basin east of Greenland. Let's just watch and see what happens to this white old sea ice. Things are just trucking along here. There's no real change to the system. We see a fair amount of old sea ice. The Beaufort Gyre is working quite well, but now we've seen a decrease in the old sea ice, and something's happening in here. We still see the Beaufort Gyre working, but there's a marked decrease in the amount of old sea ice. And we're going to see a really drastic change coming up. Look at this. Hardly any old sea ice left. So what we saw in that movie is shown in this graph. Time is along the bottom, and the vertical axis is the area in square kilometers of sea ice in the summer. The red line charts a decreasing areal extent of summer sea ice in the Arctic Ocean from the late 1970s to 2019. Note the significant decrease in area occurring in around 2006, as we saw in the movie we just watched. If you're a polar bear dependent on the existence of sea ice to hunt seals, you probably need to adapt to that change. So let's shift our attention to neighboring Greenland. This movie investigates what's currently happening and models what will happen to the Greenland ice sheet. Listen in to the commentary if you can hear it, and apologies, as I say, if the soundtrack's not good on your end.
It's easy to imagine Greenland as a land of perpetual ice. However, scientists have recently estimated that the Greenland ice sheet may be gone within the millennium.
My name is Andy Aschwand, and I'm a glaciologist with the University of Alaska Fairbanks. I work at the Geophysical Institute.
Andy and his colleagues have used data collected by NASA to model some of the possible futures of the Greenland ice sheet.
So we see our projection of how the Greenland ice sheet will retreat over the course of the next roughly 300 years. It's really cool that now we can actually watch in the animation, in the simulation, how we think it behaves. I mean, we put the best physics possible in there, and we can actually watch what could happen. And that's something we could not have done before. NASA's Operation Icebridge over the past decade has been instrumental in gathering data sets that help drive our modeling.
This model gives us a more accurate picture of how greenhouse gas emissions may affect Greenland and us in the future.
Of the three scenarios that we tested was one like sort of a low emission, medium emission, and high emission scenario. And at the moment, it looks like we are on the highest scenario. The three different scenarios lead to basically three different futures, three different Greenlands. If we choose the path we are on right now, or if we stay on that path, there's actually a good chance that within 1,000 years or so, the whole ice sheet will be gone.
These scenarios show that the melting ice could contribute at least 80% more sea level rise than previous estimates. This model helps us understand the dynamic nature of the Greenland ice sheet and arms us with the knowledge we need to inform our future.
I hope you enjoyed that. We're going to shift poles. Although global warming is most emphasized in the north, there's also effects in the south. And this little video shows what's happening to the Antarctic ice sheet. I can't do anything about the music. So red is melting and blue is accumulating. we see a lot of melting on the left. So combined, about 7 millimeters of sea level rise associated with melting in the Antarctic. This slide, basically, it's an explanation of why we see melting in the Antarctic. And it's largely due to changing current patterns in the circumpolar deep water around the Antarctic continent. We get warmer waters coming in and they undercut the edge of the Antarctic ice and basically erode it from the bottom rather than melting it from the top. So changing ocean currents, warming ocean currents are affecting the Antarctic. The water from all this melting ice ends up in the ocean, which prompts us to look at sea level. The upper two graphs in this slide should be familiar to you by now if you've been following these talks. They show the change in atmospheric temperature through time and of carbon dioxide. And we've already commented on the apparent correlation between those and also said, warned ourselves that correlation doesn't necessarily mean causation. The bottom graph is new to us. It shows the change in global sea level over the same time period. Note the correlation between rising temperature, here, 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 and rising sea level. This is high temperature is high sea level, low temperature is low sea level. This is because during cold periods, a lot of water is stored in continental ice sheets. In the transition to the warm periods, this ice melts, the water flows into the oceans, and the sea level rises. We're going to look a bit closer at this transition from the last glacial maximum here up to where we are today. We can see a significant sea level rise associated with the rise in temperature. On the left, these are obviously maps of the world. There's one for 20,000 years before present and one for today below. The ice has been removed just so we can see what's going on with regards to the land and sea level. 20,000 years ago, sea level was 120 meters below what it is today. And there were significant differences in the outlines of the land masses. I've just outlined them here. Most significant areas of difference are areas with the present Bering Strait, the Canadian Arctic Islands stretching across to Greenland, Western Europe, and down here, Southeast Asia, Australasia. At the glacial maximum, the northern areas up in here, they were covered with ice. When the ice melted, there were temporary land bridges here. These land bridges were important in that they facilitated migration of plants and animals, including humans. The chart on the right shows the sea level rise through time from this map to the present day. We see that sea level rise occurred rapidly in a series of meltwater pulses. These were associated with warming periods. So what's happening today? This graph shows observed sea level rise since 1900. Time on the horizontal axis, the amount of sea level rise on the vertical axis. Since 1900, sea level is shown to have risen 175 millimeters, or 17.5 centimeters. The rate of sea level rise is shown to be accelerating through time with a significant uptick in about 1995. Now, there's a word of caution about this. 1995 coincides with when we started getting satellite imagery, giving us very accurate sea level estimates, sea surface readings. So there may be a certain amount of sampling bias in this curve, but what is definite is that sea level is rising. And today it's rising at about 4.4 millimeters a year. So how much will it rise? This graph illustrates possible ranges of sea level rise as predicted by modeling. It says that we can predict, depending on what climate model one believes, green, orange, or red, a difference in sea level rise of between 30 centimeters to 2.5 meters compared to the sea level in the year 2000 by the year 2100. It's a pretty big range, and it obviously indicates there's a fair amount of uncertainty. So what areas in the world are going to be affected? Well, obviously the coastal areas, but especially low-lying coastal areas, such as here, over in here, and well, anywhere where the shoreline is low. Florida is going to be severely affected. Gulf of Mexico, US states, Texas, Louisiana are going to be significantly affected because they're low-lying coastal areas.
Richmond?
Yeah, just wait. So how many people are going to be affected by this? This map shows those countries that will be most affected by sea level rise, listed in order of the size of population affected. In total, about 250 million people will be directly affected physically by sea level rise. That's a lot of people. China heads the pack with over 50 million people affected, followed by Vietnam, Japan, India, Bangladesh, and Indonesia, all of those countries with more than 10 million people affected in each of them. Europe is, look at the United Kingdom, 2.6 million, 3 million in the United States. So it's not just a third world problem. Let's look closely at one of the low-lying areas that will be severely affected. Bangladesh, we saw from the previous slide, will have about 10 million people directly affected by sea level rise. And this is because it has a significant population living in the low-lying delta of a giant river complex, which includes the Meghna, Padma, Brahmaputra, and Ganges. The three slides we see, the three maps we see on this slide show very different scenarios. This is the current scenario in here. It shows very heavily populated areas in low-lying lands. The middle map shows a 1 meter sea level rise, and it shows 15 million people being affected and 17,000 square kilometers of land being submerged. If sea level goes up by 1.5 meters, 19 million people will be affected and 22,000 square kilometers of land will be submerged. 19 million people is half the population of Canada. Talking about Canada, Vancouver will be affected. Take a look at these maps. On top, this is the present sea level map of Vancouver. On the bottom, we look at a map showing what areas will be affected by a 1 meter sea level rise. The blue areas are areas that are subject to inundation. Don't expect to land your airplane in Vancouver Airport. And if you live in Richmond and in parts of Surrey, you'll have a problem. But of course, the local municipalities are not unaware of this risk. This shows, the inset map in here shows a system of dikes in place and being built to protect Greater Vancouver areas from sea level rise and storm surges. By the way, the big windstorm the other day had a storm surge which coincided with a king tide, and that's a recipe for flooding. This is the photograph you see here is a Google Maps photo of part of the Richmond dike system, which is a large construction project to mitigate the effects of sea level rise. And it's already costing big bucks. This was a 2017 headline. $300 million dike plan forges ahead. I wouldn't be surprised if this whole complex here costs over $1 billion. How will it affect us closer to home? In other words, Ladysmith, how will we be affected by sea level rise? Well, generally our shorelines are steeper here, so the effects will be less noticeable or impactful. Now, I haven't seen any specific reports commissioned by council on this, but as we shall see, sea level rise is included amongst the anticipated effects of climate change in Ladysmith's official community plan. I put on this map what I suspect are vulnerabilities such as flooding and erosion associated with sea level rise in the Ladysmith Harbor area. Low-level areas will be flooded, the gray infills to the red circles, and we could expect significant erosion in the yellow circles in here. The head of the harbor, which is low-lying, will experience flooding. And this area here, which is called Slack Point, which is just slightly above sea level, will be both eroded and flooded. Let's look at Canada, an overview of Canada. This is a map of anticipated sea level changes affecting Canadian coasts by 2100. Red, we can expect a sea level change of 75 centimeters to a meter, grading all the way down through the colors to, surprise, surprise, negative sea level rise. In other words, the sea level is apparently going down. So how does that happen? We can see most of the sea level going down is in this north central coastal area and Arctic area. What's going on? Well, what's happening is that these are the areas which had the maximum ice cover in the last glaciation. And they were subject to the massive weight of those continental ice sheets. Subsequent to the melting of those ice sheets, the ground is bobbing up like a cork. Now the weight is gone. And what we're getting is post-glacial isostatic rebound in these areas. So although the overall ocean level is rising, the land here is rising faster. So there's an apparent lowering of sea level in this area here. But on the west coasts and east coasts, we're going to experience sea level rise because the rebound effect is less. You can imagine if you lived in Resolute Bay here, you'd be less worried about sea level rise than if you live over here in Richmond. Let's take a look at about how the land area of Canada is being affected by global warming. This slide shows the actual change in average temperature for areas in Canada for the period 1948 to 2012. The hotter colors indicate higher temperature rises. First note, there's no area with decreased average temperatures. Everywhere there's been a recorded temperature increase. Note also the biggest temperature increases have been in the Northwest Territories and Arctic regions. And this temperature rise gradually decreases as you go further south into the prairies. But right here, this is the guts of it right here. Northern Northwest Territories and down into the prairies. This slide shows a predicted temperature rise for Canada by the year 2080 for the month of December. The darkest colors are the highest temperature rises. We see the highest rise centered on the central Arctic, where there's more than 10 degrees of increase anticipated for December temperatures. Temperature rise is reduced to the south, with the inland portion of the country in general experiencing an increase of 5 degrees or more during the month of December. The coastal provinces, BC included, see a rise of about 3 degrees. So according to this model, we can expect the winters to be noticeably warmer. Obviously, changes in average winter temperature of this magnitude will bring significant physical and biological changes. Our environment, landscapes, wildlife, ways of life, and agriculture will be affected. This map shows the distribution of some of the more important effects of climate change across the country. We've already seen changes in the Arctic sea ice up here. Talking about animals, it says changing animal distributions affecting food supply for indigenous populations. Just the other day, I read an article on CBC Online News about how caribou are calving earlier and Arctic bird migration routes are changing. We're going to take a closer look at permafrost and forests. This map shows in purple the current distribution of permafrost in the Arctic regions. Purple is solid permafrost. Obviously, as you go further south, you get warmer and the permafrost begins to break up until it disappears completely. Much of northern Canada is underlain by permafrost. This distribution is being affected by global warming. Apart from the physical changes in the landscape, such as these giant potholes, which result from thawing of the frozen ground, organic matter in the previously frozen sediments is oxidized, and significant quantities of carbon dioxide and methane are released into the atmosphere. There's a person for scale in this, so you can see the wholesale collapse of the permafrost in this area of the Arctic. The release of CO2 and methane through the thawing of permafrost is a major source of greenhouse gas, and it just exacerbates the overall greenhouse gas situation. Infrastructure is also being affected. Buildings are being rendered unstable as the permafrost on which their foundations stand thaws out. Traditionally, this was due to poor engineering and insufficient insulation. However, global warming is causing mass thawing of permafrost and instability of buildings and also of infrastructure. This is a road in the Northwest Territories, which is suffering from thaw of permafrost on which it was built. Of course, melting ice isn't just restricted to the Arctic. I suppose many of us are familiar with the well-documented retreat of glaciers in the Canadian Rockies. This is the Athabasca Glacier, which has been in major retreat since about 1870. We can see its extent here, 1870, 1917, 1977, and back where it is now. These are just photographs taken from the same spot, 1924, you're pretty close. 1985, it's gone back, and 2011, it's way back. 2020 is probably way further back again. Let's move from ice to fire. Forest fires, although a natural phenomenon and a necessary part of our forest ecology, are argued by many to be of greater frequency and intensity than previously due to climate change-induced drought. However, the picture isn't clear, as exemplified by this, at first, indecipherable graph. The brown arrow, which is a linear count of the number of forest fires through time, indicates that there is an actual decrease in the number of forest fires. The green arrow, which is the area burned by the forest fires, is relatively flat, maybe slightly going down. So the inference, sort of, by this slide, although it's unconvincing, is maybe there's less forest fires, but larger forest fires in Canada through time. Some forestry experts actually say that the evidence favors a reduction in forest fires over the past 30 years, and state that this is likely due to a higher carbon dioxide content in the atmosphere, which is invigorating plant growth. So the jury's out. What is the effect in Canada of global warming on forest fires. However, if you live in Australia, you might have a different perspective on things. The incredibly destructive fires in Australia in early 2020 are blamed by many on climate change-induced drought. Look at the colossal area burned in Australia over the 2019-2020 transition, 63,000 square kilometers. This makes our Fort McMurray area of a mere 6,000 square kilometers look puny. But of course, Fort McMurray was just a single fire, not the entire Australian fire compound. And if you're in Fort McMurray, you wouldn't think that was a puny forest fire. Of course, closer in time are the huge fires which were recently experienced in the Western US this summer, from which we benefited by receiving the smoke. These are blamed by many on global warming and drought. And just to show you how important a factor forest fires are globally, this is a slide of the, showing the world on a single day, October the 26th, 2019, and all the forest fires that occurred in the world on that day. So fires aren't the only thing affecting our forests. Milder winter temperatures are facilitating the spread of pests such as pine bark beetle across the northern forests. The brown trees in this photo have been killed by the beetle. This inset map shows the eastern spread of the pine beetle across the Rockies into Alberta. The dark area is the traditional range of the beetle. The lighter gray is the expanded range, and the lightest gray is where they possibly are. So we can see a massive increase in distribution of the pine beetle due to ameliorating temperatures in the winter. It simply isn't cold enough in the winter to kill them off. This infestation, along with that of the spruce beetle, leave many dead trees, which are tinder for forest fires if not harvested. So maybe this is why there appears to be fewer but larger forest fires in Canada. Climate change induced drought is also blamed for an ongoing change in our local vegetation. We're seeing a die-off of drought-intolerant species, such as western red cedar and salal. Here's a bunch of dying cedar trees in here, and here's salal succumbing. Just take a look around as you walk in our local woods. You'll see the cedars are in pretty rough shape. So we've looked at some of the effects of global warming and a little bit at what we might expect in the future. What are we doing to compensate and prepare for it? For an in-depth study on the effects of global warming on the Carrichon Valley, take a look at this report. You can get it online. The title is Climate Projections for the Carrichon Valley Regional District. And this phase 1 of this report has been completed, and it's climate projections and impacts analysis. It's the first of 4 planned phases relating to what is called the new normal Carrichon. Detailed climate projections for our area are provided in the phase 1 report. The bottom line is hotter, drier summers, warmer, wetter falls and winters, and precipitation being focused in isolated, more intense events. The CVRD has also produced pamphlets to assist the public in recognizing the risks associated with climate change and what to do to reduce exposure to these risks. Again, you can get this online. The pamphlet emphasizes risks associated with increased intensity of winter storms, hotter, drier summers, and rising sea levels. Coming closer to my home, anyway, the town of Ladysmith has a strategic plan. This is the 2020 to 2023 strategic plan. and it contains a section entitled Action on Climate Change. The town is taking a proactive approach to the effects of climate change. These include measures to reduce greenhouse gas emissions and reduce energy requirements. Emission reduction is addressed through encouragement of active forms of transportation, building of walking and bike trails, things like that. Encouraging renewable energy options for buildings, installing electric vehicle charging stations, and introducing guidelines for increasing building energy efficiencies. Also included are measures to accommodate changing weather patterns, and these include water management, increased storage capacity, municipal and domestic, to avoid shortfall in times of drought, and also increasing the size of the drain network to handle the more intense winter deluges to be anticipated. So that pretty much wraps up my talk. So I hope they've been useful to you. Researching them has taught me a lot. And the main points I'd like to leave with you are as follows. Global warming is already significantly affecting our environment. Globally, we need to prepare for more weather extremes, increased food insecurity, and associated social unrest. In Canada, in Ladysmith, we need to prepare for a changing north, drying prairies and changing forests, droughts, increased wildfires and smoke pollution, coastal and river flooding and erosion, and extreme weather events. We can take some solace in the fact that local government is taking a proactive approach. Do check out the online information. What have I come away with? As a geologist, I already knew that climate change is a natural continuum. What I wasn't aware of was the magnitude of effect our activities are having on the environment, apparently manifested in recent global warming. I certainly wasn't aware that we were pumping 36 billion tons of carbon dioxide or greenhouse gases into the atmosphere every year. Big picture takeaways for me also include we can't continue to pump pollutants into the atmosphere and oceans. We need to think very hard about the sustainability of our current practices. This applies to our physical environment, but also as well to our biosphere. Global warming is with us, and we cannot stop it. And global warming is only one aspect of the challenges we're facing today. The problems facing Earth's ecosystems are immense. Apolitical international cooperation is required, but together we can make the world Greta again.